What's going on, guys? It's Mr. Jones again. Today we're going to talk about the first task of Chapter 2. So Chapter 1 is a little wonky in my opinion, and so I just kind of try and get a few things out of it and then just move right along. So the last video you should have watched was the PowerPoint about what the heck is a quadratic. And we've also done some review on area and perimeter, so make sure you check that video out again. It's on YouTube, right? So you can fast forward it and speed me up. But just to kind of get an idea of what we're talking about if you're super confused. So, with that being said, let's go ahead and talk about this task. So, you'll notice this task is called 2.1 Transformers Shifty Wise. So, they always have some kind of catchy name, right? This is again a develop understanding task. So keep in mind that a develop understanding task again means that it's going to be difficult. There's going to be a bunch of new things, but this is actually a really cool task, in my opinion. I think that this task is one of the neatest ones because we're going to talk about Desmos. So let's move right along. Optima Prime is designing a robot quilt for her new grandson. She plans for the robot to have a square face. The amount of fabric that she needs for the face will depend on the area of the face. So Optima decides to model the area of the robot's face mathematically. Of course, why wouldn't she, right? She knows that the area, which we're going to represent with the capital A, of a square with the side length of x units, which we can call centimeters or inches, is modeled by the function a of x equals x squared. Square units, square inches, square centimeters, whatever. But let's not worry about that part of it. Okay, so this is the equation that we're going to use. Remember, A is the area, A is area, and x squared is represented by a square block. This is the original square face. This is my best square I can draw. And the side lengths of that block are x's. That's a horrible x. Let's try that again. X's. So we know squares have an area. Sorry, we know squares have all the same side lengths, and those side lengths are x's. And if you got the area of that, x times x, right? Length times width or base times height. X times x is x squared. So that's how we get this equation here. Okay? By the way, in all these problems, remember, this is the parent function. This is where all quadratics come from. So we always start off with this square whenever we do other things. I'm going to mention that over and over, but keep in mind this x squared block, this x by x block is going to come up over and over. We're going to begin here every single time. All right, with all that being said, let's just talk about this first question. What is the domain of the function in this context? So that means like, let's just talk about what domain means, right? If you forgot, domain is all possible x values, all x values that are possible in this equation, in this problem, whatever. So any x value. So if you think about x being the side lengths over here of this square, what are possible x values in this context means in this problem, in the way that we're talking about it. So could x be 3? Sure, you can have a side length of 3 or a side length of 7 or a side length of 436, right? But could you have negative 3? A side length of negative 3. It doesn't make sense, does it? How do you measure something negative 3 feet, right? So the domain or the possible x values in this context is all positive numbers, right? Positive. I'll put a U there. All positive numbers, right? Any number, all the way that you can think of as high as you can go, is possible. All right. So that's the possibility of what the area could be, any positive number. All right, this next section tends to always kind of, I don't know, students always kind of have a hard time understanding what's going on. So I want to stress again that you always start with this basic square that's still drawn on the screen, the x by x squared, the area of x squared. So you have two pieces of information here. You have a side length of x, and then you also have an area of x squared. So keep that in mind. So what we do is look down here at question 2. I'll put a circle around it so you know where we're at. And it says match each statement. So you see there's 4 statements about the area to the function that models it. So over here on the far right, these functions are all a of x equals. They should say a of x, but they're all representing the area. So you have these areas of these 4 squares, right? And on the left-hand side are statements that match it. A couple of the statements are talking about changing the side lengths, and a couple of the statements are talking about changing the area itself. Remember, you start off with the basic x by x square. So draw that on your paper, okay, and see if you can figure out, hey, if I changed what it's saying about the length of the sides, how would it make the area look? Remember, area is length times width or base times height, right? In this case, it's a square, so you can just take whatever one of the side lengths are and square it, and that's what the area is going to be. So give it a shot. See if you can match A, B, C, D, all those functions on the right, with the statement on the left. So take your time. Pause me. Okay, hopefully you gave this a really good shot. You can always change your answer. That's how you learn the most, is by making mistakes. So if you didn't, pause me now. I'm going to go over the answers. All right, here we go. Remembering that we're starting off with the x by x, right? So I'm just going to go ahead and redraw it really quick. So here's the better square that I drew, an x by x square. And remember, the area is up here, right? Underlined in black and orange now, right? Go Woodlake. All right, so here we go. Let's read the first statement. The length of each side, so we still have a square here, the length of each side is increased by 5 units. So right now it's x units. If we wanted to increase it by 5 units, it would look like that. And it said each side. Now we're worried about what the area of that's going to look like, right? What is the area of a square? Just whatever one of the side lengths is squared. So my side length of x plus 5, square the entire thing, and that's the one that matched. So the very first one, the length of each side is increased by 5. The new area should look like B, like boy. All right, next one. All right, the next statement says the length of each side is multiplied by 5 units. And by the way, if you're starting to see what's up and you want to pause again during this, you should, and see if you can fix your answers and make sure you're doing them right. You always want to see if you can figure it out on your own first. All right, if you can. So how do we multiply each side? Boom, 5x, 5x. All right, now the entire side, 5x, needs to be squared to find the area. So that answer is C, right? That's what C looks like. All right, next one. All right, this next one says the area of a square is increased by 5 square units. So remember, not only are we starting with this x by x square, we're also starting off with the equation that we had up top, right? So now it's saying, hey, if you have this equation, a of x equals x squared, and I take that area and I increase it by 5 units, now it's going to look like that, right? All we do is add 5 to the area. So that one is D. Now, obviously, if you just use process of elimination, this one should be A. So let's just prove that it is. Let's start off again with the original parent function and then read the statement. The area of a square is multiplied by 5. So this entire area is multiplied by 5. If I can squeeze it in there, the entire x squared is multiplied by 5. And sure enough, that is what A said. So good job. If hopefully you learned some stuff, and if you made some mistakes, you learn from those. All right. Now, of course, optima. I remember we're dealing with optima. the woman that's making the quilts, right? She's a nerd. She loves math. And she started thinking about the graph of y equals x squared, okay, in the domain of all real numbers. So she cares about negatives and positives now, not just about her quilts. And she's wondering about how changing the equation of the function, like adding 5 or multiplying by 5, like we did in this last section, how it affects the graph. So she decided to make predictions about the effects and then check them out. So the first thing we're going to do, we're going to of course follow in Optima's footsteps. She's our idol. We're going to predict. So clearly number 3 says predict how the graph of each of the following equations will be the same or different from the graph of y equals x squared. So remember, you've seen what the parent function looks like in the PowerPoint presentation from last time we had class. And you know the basic shape. If you forgot, go take a look. But basically, remember, it goes like this, right? And it goes through. That's horrible. I'm not going to be able to draw it, but this part is at the origin, right? In the parent function, it's at the 0, 0. So how do you think the parent function graph, y equals x squared, is going to differ or be the same from these 4 graphs? Okay, so you can make a table like this, but you're going to need room to write in these sections. I'm looking for you to write what you think is going to be similar and what you think is going to be different. So for example, look at y equals x squared and say, okay, I know what the graph looks like. What do I think multiplying it by 5 is going to do? How do I think it's going to be the same? And then how do I think it's going to be different? And then the next section, the next equation, how do I think the parent function, what do I think adding by 5 and then squaring it? So adding the side length by 5 and squaring it. How do I think that's going to change the graph? What's going to be similar and what's going to be different. The cool thing about this, guys, is you could pretty much write whatever you want, but just try and think what you really think is going to happen, how you think the graph is or isn't going to change. So give it your best shot. You should pause the video, but in your notes, I expect to see a similarity and a difference for each 4 of these graphs on the left-hand side. Okay, so now we all know that we're going to get to test it out. So the way we're going to test it out is through Desmos. So if you know how to use Desmos, go ahead and open up that tab on your computer. But if not, I'm going to give a quick little tour on how to do it. All right, so if you look up on the top here, it says desmos.com. You're going to go ahead and go there. And then the screen will pop up, and you're going to click on Graphing Calculator. So go ahead right here, this blue section, Graphing Calculator, go ahead and click it. And then this is going to open up. And if you scroll in and out, you can get closer and further from your graph. This is the important section over here on the left. You just type in your equations. So I'm going to help you out and type in x squared. There's a couple ways to do it. First of all, this is the same x as the one on your keyboard. And then if you hold shift and then the number 6, it takes you to the exponent and you can put a 2 there. So at the number 6 looks like a little hat, a little pointy carrot looking thing. So that's what is the to the symbol. If that's really confusing to you, you can go down in the far left-hand corner. Mine's kind of being covered by my stuff there, but it's a keyboard. And then you can see the a squared button. So you can also type it in. If I typed in x and then hit this squared button, or you can type x and then this a to the b button and then put in whatever power you want. So those are all 3 different ways that you can type it in. So we only need it once. And notice that I didn't put a y equals, but if you do, it doesn't change anything. So this already assumes that every equation says y equals. So what we're going to do here is we're going to do a bunch of stuff on Desmos. So make sure you have Desmos up, because you're going to be comparing the parent function here. You're going to leave this on your screen the entire time. So leave this as function number 1, and you're always just going to change function number 2 or 3 and see how they're all different, but don't take away the parent function, because the questions are always going to be, how did the parent function change? Okay? All right, so here's what the first problem is going to look like, right? And I'll cut and paste it real quick and post it so you can see, but I'm just going to explain what it's talking about. So it says Optima decided to test her ideas using technology, aka Desmos, right? She thinks that it's always a good idea to start simple, so she decides to go with x squared plus 5. So she wants to change her parent function, but remember, don't remove it on Desmos. This is your next function. And she graphs it, see, along with the parent function in the same window, so on the same screen. Test it yourself and describe what you find. So right now, go ahead and go to Desmos, give it a shot, and put it in together and see what you find. Okay, see what you find. All right, so here it is. I put it in on Desmos. My red graph today will be my parent function, and then the other colors will be the other function. So I typed in x squared plus 5, and I noticed that the parabola is up there, right? And so there's some questions about, is it the same shape? You can drag it around, see what's going on. It looks to me to be the same shape. So then you kind of think about, okay, well, what did that 5 make the equation do, right? All right, so here's the next question. All right, knowing that things make a lot more sense with more representation, so we saw what happened by adding 5, Optima tries a few more examples like x squared plus 2 and x squared minus 3. Okay, and looking at both the table and the graph for each. I think the graph is enough. Okay, what conclusion would you draw about the effect of either adding or subtracting a number to the original parent function? So we're going to practice adding numbers or subtracting numbers. Okay, and then eventually we're going to come to a conclusion like, hey, if I add a number, it does this. If I subtract a number, it does this. And we're going to realize that we're just going to call that number on the end k. So basically, what can you say about adding or subtracting a number? And make sure you're as specific as possible. So now's your chance to go into Desmos. So you don't have to only use plus 2 or minus 3. You can use other numbers if you want, but plug in values like positive 2 or negative 3 and see what you can conclude about adding k and what it does. All right, so hopefully you got some good answers for the last section. I'm not going to give you the answers yet because I want you to actually do a decent job and try and figure it out and show me what you did. We'll talk about the answers later. All right, so here's the next one. After her amazing success with addition in the last problem, Optima decides to look at what happens with addition and subtraction inside the parentheses, or as she says it, adding to the x before it gets squared. Okay, so inside the parentheses. Using your technology, aka Desmos, decide the effect of h in the equation, x plus h squared or x minus h squared, okay? And then record a few examples and then explain why this effect on the graph occurs. So basically, I want you to plug in some numbers for h. So here's the equation. Plug in some numbers, and I gave you a couple examples of values you can choose, a positive one and a negative one. And of course, you can choose whatever numbers you want, but I want you to tell me specifically what changing h does to the graph. So go ahead and do that now, guys. Okay, by the way, really quick, your explanation and your notes should be able to say what numbers you chose. So I chose plus 2 and plus 3 and minus 6, and this is what happened. This is how far it went in this direction or whatever. So you need to be as specific as possible so I know you went in Desmos and tried some stuff out. All right, so now that you had a chance to do all that, hopefully, here are the last two things Optima wants to know. The things that we can change about the parent function of y equals x squared. Remember, that's the equation we're always changing, right? So she said number 6 was very tricky. So hopefully you realized it was kind of a little bit different than you expected. And she hopes that multiplication was going to be more straightforward. So she decides to start simple and multiply by -1. So she begins with this equation, y equals -x squared. Before you put it in, predict what the effect is on the graph and then test it. Okay, why does it have this effect? So why is it having this effect? So go ahead and pause the video and answer that. Go find out what adding the negative up front did to the graph. All right, now that you've had a chance to do that, let's do number 8. Last problem. Optima's encouraged because that one was so easy, right? She decided to end her investigation for the day by determining the effect of a multiplier. So adding an a in the front. So just like this equation, an a is about to be some number. Using both positive and negative numbers, fractions, and integers. Okay, so integers, 1, 2, 3, 4, -1, -2, and then also fractions. So we want to know what happens if we plug in a fraction up front. Well, let's start with an integer. So let's say what happens if we do 3x squared or 4x squared, right? What happens if we do -3x squared? Whoop, -3x squared. What happens if we do 1/2 squared x squared or 1/4 x squared? And what happens if we make them negative, right? So -1, I'll just put 1/3 x squared. What does that do, right? So here's a whole bunch of numbers and examples of things you can plug in. Make sure you try those. Try your own, though. See what big numbers like 10, 20, 30, or 100 might do. Okay, so this is your chance to be creative and figure some stuff out. And this is where you can kind of find math fun, is whenever you get to discover it on your own. All right, guys, hopefully you got pretty familiar with Desmos today. You saw some cool graphs. You figured some stuff out. Tune in next time where we talk about the answers and this new form that we're going to talk about. And we'll learn all about what the H and the K and the A and all that did. And we're going to have some good notes on that. So make sure you show me all the work you did today in your exploration, and I'll give you the new notes coming up soon. Later, guys.